Hi guys, I wanted to give you a quick little insight into kind of how to use these equations in terms of when we go ahead and look at a change in momentum and we start looking at acceleration, we start looking at impulse. One of the biggest things you need to keep track of is direction. This is where that frame of reference thing we talked about before ends up being a crucial piece of this. So direction matters when it's coming in versus coming out off of, say, a tennis ball colliding with a wall, like you can see here in the diagram. So the diagram below depicts the change in velocity of a ball that undergoes a collision with a wall. Indicate which case, A or B, has the greatest change in velocity, the greatest acceleration, the greatest momentum change, and the greatest impulse. And it wants you to support each answer. And the best way to go ahead and do this is start by taking a look at some of these equations. So first thing we want to take a look at is the equation for momentum, and that's going to be P equals mv, so mass times velocity. So in this particular instance, it doesn't give us the masses of the balls, but what we can go ahead and do is realize that momentum in equals momentum out. Um, if it doesn't, then we're not dealing with a truly elastic collision. So if we're going to look at delta V, which is the first one it asks for, which is the change in velocity, what we have to realize is that VI and VF are what we're looking at. In this case, we have to identify which direction is going to be positive. If we assume that positive is going into the wall, then we have to realize that going away from the wall is going to be negative. And so if we say our initial velocity is going to be 10 meters per second, we have to say that our final velocity is going to equal negative 5 meters per second because it's in the opposite direction. So if we substitute that in here, we've got negative 5 meters per second minus 10 meters per second. So our delta V here is going to be negative 15 meters per second. So that's our gap that we're looking at in terms of our delta V. If we look at our other instance, we're going to do the same setup. We've got positive going into the wall, negative coming away from the wall. And we go ahead and take a look at our minus 28 meters per second minus 30 meters per second, which is going to go ahead and give us negative 58 meters per second. So the change in velocity is obviously going to be greatest here in case B, because as you can see, the change in velocity is 58 versus 15 meters per second. Okay, so greater change in velocity. And you can say see work above. And this is the big thing I want you guys to do is I want to make sure that you're going ahead and you're working these problems out so that I can see what it is that you're doing. Now, if we're looking at a change in velocity, right? So change in velocity is equal to an acceleration. So if our greatest change in velocity is b, then our greatest acceleration should also be b because a equals vf minus vi over t. Okay, so that's our average acceleration when we go ahead and start looking at that. And that's why we get the units meters per second, because meters per second is velocity over time. And so the only thing that may change this is how quickly this happens. But if we assume that t for time is equal in both circumstances, t for case A and t for case B are the same, then what we're really looking at is how big that change in velocity is. So now we have to go ahead and take a look at the greatest change in momentum. Now, remember that momentum is equal to mass times velocity. And so if our masses are going to remain constant, which I'm going to assume they do in these cases, we're dealing with tennis ball in both cases, then if the momentum is based on mass and velocity, and change in momentum is change in velocity, we just calculated the change in velocity, and it was greater when we were going to go ahead and take a look at case B, then our change in momentum has to be in case B as well. And the reason for that is the greater velocity. Now, when we go ahead and take a look at force times delta t, that change in time, this is going to be our impulse, right? Impulse. And that's going to depend, again, on how much time it takes. If we assume in this particular example that the time is the same, the time is going to be the force is going to be bigger on one versus the other, because if we say that the mass is the same, then we have a greater change in velocity for case B. That means our impulse is going to be bigger for case B. And so therefore, if we assume the times are the same for these two instances, then this would also need to be case B. But we understand that that's because F delta T is equal to m delta v. All right. And so the greater change in velocity, if the mass is held constant and time is held constant, means the greater force. And therefore, we have the greatest impulse with the same one, since the two factors are the same. And then momentum, remember, again, because this is P equals mv or m delta v, then the larger the delta v, the larger the P. Okay, so the next part I want to go ahead and take a look at is when we go ahead and start looking at trying to apply this to a realistic situation. Remember, none of this will be perfect. We have that little bit of that spherical cow thing coming in, because we're going to go ahead and assume, as we go ahead and take a look at these, that we have a perfect collision, that we're not going to go ahead and lose sound or heat or light energy from the particular system. So it's a closed system. All right, so two train cars of identical mass, M1 equals 10 kilograms, M2 equals 10 kilograms, collide and move off as shown. So this is where we're going to have to learn to use these two collisions for elastic and inelastic. If they separate like this, that separation is going to be for an elastic collision. Okay, because they separate, and you can see here we have M1 V1, M2 V2. Okay, and that means in the final case they're not connected to each other, whereas in the elastic collision you've got m1 plus m2 and then v final, which is a combined final velocity. Okay, so again, if we go ahead and say that m1 is 10.0 kilograms and m2 is 10.0 kilograms, we need to go ahead and talk about our velocities. The left car was initially traveling at 2.0 meters per second, and that's headed to the right. And the right car was initially traveling at 3.0 meters per second, and that's heading to the left. Now, again, we need to determine what is a positive and negative direction. Now, it is our tendency to go ahead and say that right is going to be the positive direction, but I don't care if you use the other one as long as you're consistent, and that reflects when you go ahead and do your answers. So I'm going to say that this is a positive and this is a negative direction. And then we can go ahead and set up at least the first half of our elastic collisions equation. So we've got M1, which we said they both weigh 10.0 kilograms, times V1 initial, which we just said was 2.0 meters per second, plus M2, which we just said was 10.0 kilograms, V2 initial, which we just said was negative 3.0 meters per second. And that's going to be the first half of this equation. Okay. So again, what you're looking at is this idea of momentum before is equal to momentum after. Okay. So that's what we're trying to say, because we have this collision equation and we're relating it in terms of momentum. Now, let's read the rest of the question. After the collision, the left car is traveling at a velocity of 2.5 meters to the left. Okay, so the left car is now traveling at 2.5 meters per second. But now you'll notice instead of going to the right, it's going to the left. So we have to keep it consistent in terms of our frame of reference. So now we have a negative velocity. And so it wants to know what it is we're looking at here in terms of the velocity of the right car. Okay, but we'll work to get there. So first of all, what type of collision it is, because they separate, this is going to be an elastic collision. And what was the initial momentum of the right car? So the right car over here, all right, is going to be m 10.0 kilograms times velocity minus 3.0 meters per second. Okay, because remember again, momentum equals mass times velocity. So in this case, we have momentum equals 10 times -3, which is going to equal -30. And our units are important, kilogram meter per second, because it's a momentum. What was the initial momentum of the left car? Again, same setup. V equals 10.0 kilograms times, in this case, the positive 2.0 meters per second, which is going to give us initial momentum of 20 kilogram meter per second. Okay. Now, if we're going to go ahead and do that and simplify, because this is our initial momentum that we started with in the system, okay, we're going to have 20 kilogram meters per second plus a negative 30 kilogram meters per second, which gives an input momentum, or a momentum before, of negative 10 kilogram meter per second. Okay, so I'm going to go ahead and clear this off and slide down so that you guys can go ahead and continue to follow what I'm doing, but the visuals and everything we've just talked about is going to stay the same. So we slide up. What's next? What's the final momentum of the left car? And what's the final momentum of the right car? Now I'm going to move up just so you can see all these pieces again, but remember that that's what we're going to go ahead and look for here. So we just said that the net for the beginning in terms of this elastic collision is going to be, let's see, we said 30, -30, and positive 20. So 20 minus 30 is going to be -10 kilogram meters per second. So now we're on the other side, and we can go ahead and calculate the momentum for the second car, the left car, because we said that that's 2.5 meters per second to the left, and it still has that 10 kilograms. So this is car 1 after is going to be equal to 10.0 kilograms minus 2.5 meters per second. So if we move our decimal over, this is going to go ahead and give us a momentum of 25, -25 kilogram meters per second. Okay. Now, if we're going to go ahead and try and set this equal to the -10 from the other side, we can see that this is going to be -25 kilogram meters per second plus this category, which is going to be 10 kilograms V2 final. We go ahead and add 25 kilogram meters per second to both sides. We end up with 15 kilogram meter per second equals 10 kilograms. Oops, that didn't come out well. V2 final. And we divide by 10, and that ends up being 1.5 kilogram. Oops, we got rid of kilograms. 1.5 meters per second. And so that's the final velocity for car 2. 1.5 meters per second. Notice that that's positive, so that's going to be going to the right after the collision. Okay, so that's how you go ahead and do these types of equations. And the inelastic one is basically the same thing. The biggest difference is that you share a final velocity. So we can actually go ahead and determine things a little more simply in most cases. Okay. All right. So I hope that was helpful. Let me know if you have any questions. Take care of yourselves. I'll talk to you guys soon. And come see me if you have anything you need. Take care of yourselves. Bye bye.